Hello, can you hear me?
Hello, can you hear us?
Yes, I can hear you well. Thank you.
Okay, do you want to test the screen sharing? Your PowerPoint
No
slide?
problem. 1 second.
Okay, no problem.
I think it's visible now, right? And I
Yes.
can show my screen. You see my screen? The slide?
Okay, no problem. We can see the screen.
Perfect, thank you.
Okay, thank you.
Cheers.
Okay, so we'll see you at 9:10, right? The keynote
Sorry?
speakers at 9:10, right?
Yes, if
Okay,
in 12 minutes, yep,
Okay,
that's
we'll
correct.
see you later. Thank you.
Thank you, see you soon.
反正我没有关，它马上就会出事了。
不会马上出事啊，是有人要加进去的时候就会叮咚。
哦。所以全部有要关静音的，就只有那个直播的，就直播在讲的时候，其他时候都是打开。
那手机声音关小。
你要走了？拜拜。
去外面看一下。
就是 开始那个，那我要跟他说开始，但是这边的人会跟他说，所以
その後もう一個。
然后他们开始讲这个经营，顺风车是那我反正我只要想到在这个面前，然后比如说那个高考，然后他们就
然后下一个上面镭射笔，那可以看或者是就是一看看镭射笔光那个光。现在可以了。
你到时候就所以说，
9回のこれが一番
这个你说这个叫什么？
一番上で朝の9回もいっぱいなんだけど、いや全然そうだ朝なんですけど、めっちゃ9回もいっぱいだから諦める覚悟ってしょうがないからならんと。9回もってさ、9回も多分なんかあるんですよ。表彰ホールが普通にその結婚しようみたいな雰囲気になってます。
可是我觉得，我记得我们用这个修6修3就会等一下，另外两个都是非常
国際会議やってくれって言われると、 聞こえてますけど、打ち上げ続けやりたいってやってもいいですかっていつも言って続けてます。はい、めっちゃ儲けないと無理だと思います。なんかツアーかなんかに行くのか、でなければ、まあ、ノーハンドって面白いと思うんですけど、ちょっとね、ちょっと部分があるので、やろうと思うとできるんですけど、あれだと、やつないですか。低いっていうか、近くちょっともしかしたら、誰も使ってない。使ってやったら、補助金の話。
Good morning, Professor Dean.
Good morning. How are you?
It's about time we will start our keynote speech this morning.
Yep, I'm ready. Thank you.
And first of all, I want to introduce you to our guests. Ladies and gentlemen, this is the second day of our meeting. I'm very honored to host this special speech by Mission Huang from National Kaohsiung University of Science and Technology. I would like to introduce you Professor Dr. Chong Bin. He is an associate professor of energy management and control system. Also is the deputy director of admissions in WMG at the University of Warwick, UK. He's also an training fellow and an ICMT senior member. And his research interests are mechatronics systems design, modeling and control, sustainable technology for future of mobility and energy systems, energy saving, energy power management technologies, control theories and applications, renewable energy. He has generated research funding protocol about 14 million pounds for the departments. So he has published over 190 articles, including 80 high-quality journal papers. He has delivered more than 20 keynote and invited talks at the Congress and industrial events that received journal and Congress paper awards. Dr. Dean has involved in different professional activities, including technical committee member of IEEE, secretary and webmaster of IEEE CIS region, and editorial members of several international journals. General co-chair, technical program chair, and international steering committee member of several renowned conferences, including ICMT. Okay. Today, he would like to present emerging trends, standards, and the development of electric motorcycles. Let us welcome Professor Dean.
Okay, thank you very much for your nice introduction, Professor Chair. So, good morning, everyone, and I hope you enjoy the first day of the ICMT 2022 conference. And that's it, my great honor to be here today to deliver the, I think the first speak for the ICMT 2022. So, the first thing I want to give the great thanks to Professor Chair and as well as the organizing committee to make this successful conference this time, and also with the great effort to make have a very difficult, conference in the very difficult situation, especially during the pandemic. So yeah, I will start with my presentation by sharing the screen, and yeah, if we have any problem, please let me know if it's coming from my end. Okay, just double check. I hope you can see my screen. Am I right?
Yes, we can see it.
Yeah.
Thank you. I just try to put into the showing mode. Okay.
Yeah, okay, no problem. I'll mute the mic.
That's
I'll mute the mic here, okay?
That's brilliant. Thank you. Okay. So that is my topic for today. Is talking about the emerging trends and development of electric motorcycle. So this is a very popular topic where I think maybe many of you also already have experience with motorcycle, especially in Asia country, also in UK, nowadays or European country. Motorcycle is used for mainly for commuting and also for leisure. So I hope this is not really have very far from what you see from every day. So yeah, so you can see from the agenda for the talk today. The first one, I want to give you very brief trends about the next generation of motorcycle, and then after that we go to the about the development of the control system for electric motorcycle, especially with the safety critical point. And then I will give you a brief intro about our team in development of electric motorcycle within WMG department. So that is the key elements we will try to run through today. Okay. So first of all, as you know, electrification is nowadays become very popular terminology. If you can go to Google, you can easily find out from internet. Because in the over next 10 years, so the main dominance will be given to electrify application, especially to eliminate the use of internal combustion engine due to the problem with the fossil fuels and also the emission. So the government around the world already said that by 2030, approximate by at least I think 20 to 50% of all new vehicle sales need to go to electrified version in order to minimize the level of CO2. So similarly, in the motorcycle sector, the main focus given to battery electric motorcycle. So the reason why in four-wheeler, as you can see on my left-hand side, let me try to use the pointer, if it's possible. You can see from my left-hand side, if you look into the four-wheeler sector, there are lots of combination or architecture available for hybrid and electric vehicle. So you can see from the main four types, you can see series hybrid, parallel hybrid, or combined hybrid, and the last category will be battery electric vehicle. However, for motorcycle, the main focus still given to only battery electric motorcycle, even we have some small area talking about hybrid version. So the reason around that, the first point you can see that when you compare for the engine-driven motorcycle, so the electric motorcycle actually do not really have the concern about range because of the size of the vehicle as well as the shorter range. The second one is around complexity and the cost for integration. So due to the small size and also the narrow space of the motorcycles, therefore with the conversion to directly into battery electric motorcycle version, you can consider the less complexity and also low cost for conversion. Especially with the battery only, you can also consider for battery saving, space saving. And also another benefit with battery electric motorcycle, you can get the greater potential for miles achieved per minute for charging compared to the battery electric version. That's why the BEMs nowadays still will be the main focus for motorcycle. So in the next one, when you consider for the electrification, we have carried out a very simple life cycle analysis. So we base on the life cycle database from grid, and also we base on the architecture given for the engine-driven motorcycle and the electric motorcycle proportion. Based on that type of assumption, and we base on the lifetime of the motorcycle, if we assume for around 60,000 miles for about 15 years driving, and we base on the assumption that the electric version, we have only CO2 emission from the charging infrastructure, where the engine motorcycle, actually the emission can come from tank to wheel and conversely from wheel to tank. And based on that type of assumption, we carry out the life cycle analysis to understand the CO2 emission. So we consider for two phases of the motorcycle. The first phase is the manufacturing phase of cradle to gate, and the second phase is well to wheel, where you consider when it's running on the road until the end of life. So after carrying out the analysis, we can find out that the CO2 emission of the electric motorcycle in the production phase definitely higher than the CO2 emission from engine motorcycle, mainly due to the material used in electric version. However, that type of level is very small compared to the actual CO2 emission when you run the motorcycle on the road of the engine-driven version. So you can see here in my on the right side, the level of CO2 for the engine-driven motorcycle is significantly high compared to the CO2 emitted from the infrastructure for the electric motorcycle. So based on that type of calculation, we can find out that by using electric motorcycle until the end of life, you can save up to 83% of CO2 emission compared to an equivalent engine-driven motorcycle. Just for the clarity, we also carry out the analysis where you have the motorcycle running on the road from the 0 miles to the end of 60,000 miles. You can see that the CO2 level for both engine and electric motorcycle increase over time. However, the slope for the engine-driven motorcycle emission is increased significantly based on the everyday driving, where the CO2 from the electric version is only from the infrastructure. So that means when we do the calculation or the accumulation, by the end of life of the motorcycle, you can see that the electric version can save up to 14 tons of CO2 compared to the traditional one. And if you do the conversion to the duty tax you need to pay for due to the carbon emission, then actually the tax you need to pay for the electric motorcycle is only about 20 pounds per year compared to the duty charge of 104 pounds per year for the engine motorcycle. So that's a clear benefit of converting from engine-driven version into electrified version. That's why we need to consider for electrification in motorcycle. Okay. So when you move to electrification, there are a number of issues we need to consider. The first one is about the cost and range. Here I show you a number of existing electric motorcycles in the market with the two dimensions. So we can see that the E version actually coming from low cost and very short range to the high cost and also very long range. So the most expensive version you can see as on the graph or on the left side, that will be about Harley Davidson or with energy curve, where it provide you very sufficient power and also very long range of travel. Also, we have other alternative where we consider electrified version. We will be coming with the fuel cell electric vehicle. So fuel cell have the similar limitation or drawback as the four-wheeler. So the first one, if you use fuel cell electric motorcycle, we need to consider about the infrastructure, especially for hydrogen, and also about the manufacture of fuel cell, as well as the cost for fuel cell as well. So that is the key item that really limit the popularity of the fuel cell electric motorcycle. Another issue with the fuel cell system is about the lifetime. So you can easily identify that the lifetime of fuel cell and also the working efficiency of fuel cell compared to battery electric version actually significantly different. So therefore, looking forward, I think in order to make the fuel cell electric motorcycle to become the alternative solution for future, I think it will need to take about 10 to 15 years minimum in order to get it ready for the replacement of electric battery. As I mentioned, there are a number of issues we need to consider when we move to electrify motorcycle. The first one definitely will be about charging infrastructure. Currently, as you can see, we have about 3 levels very popular in the market. The level 1 is about slow charging, as you can see on my right hand side, and also it's coming with level 2 as well. The difference is only about the power level. So both level 1 and level 2 provide you solutions with AC charging, where level 3 allowing you with the rapid or ultra rapid charging mainly use the DC power cable. So the configuration between AC and DC charger has been shown in here. And with the AC charger, as you know from the concept of electric motorcycle or electric vehicle, if using AC charger, definitely we need to have a rectifier and DC-DC converter to do that. Therefore, it's linked to the issue with the weight and also cost and size of the charging mechanism on the motorcycle. So most of the motorcycle maker, if using the rectifier and the AC charging, actually they will need to use normally about 3 to 3.5 kilowatt rectifier, or they can combine them together as the zero version. They can go up to 12 kilowatt where they do the integration of 4 units. Therefore, this is increasing weight and size of the charging mechanism. If you go for the DC charging solution, the Hi-Lai or Angelica offer you the higher and from rapid to ultra rapid charging solution. The fastest rate you can see from here will be up to 48 kilowatt for Angelica Ego Plus. So that's allow you to do very short charging. And on the right side, you can see the number of charging protocol you can see from here. However, the most popular connector at the moment, as you can see, this is Type 2 connector, and also we have the CCS2 connector type is the most popular nowadays in Europe and UK. But, however, with the global acceptance of the connector type at the moment, we haven't identify a unique charging protocol. So, moving forward, if you want to popularize the number of motorcycles with electric version, the consideration of charging infrastructure is the key as well. The next part is around the autonomy in electric motorcycle. So similar to four-wheeler application, we also have the autonomy level for motorcycle. So a number of manufacturers already consider level 0 or level 1, where they consider for like driving assistant. For example, you can find out from my slide, we have the adaptive cruise control, or we have the some car warning or car monitoring system, or even some car parking assistant. Going higher for the autonomy level, say from level 3 to level 5. So there are only a few OEM considering this one. For example, like BMW, I can see on my right hand side, or Yamaha or Honda, they consider about some like self-balancing function and also some autonomous driving function. For example, like BMW, they provide that type of fully autonomous vehicle. So you can see that type of fully autonomous version may be useful for good transport or service in the future. However, we have many issues we need to consider, especially about safety and reliability of the mechanism. So the critical challenge in autonomy for two-wheeler, first one is about the self-balancing function, because if you want to drive autonomously with the motorcycle, you need to make it balance firstly. So normally the basic principle based on gyroscope, that's one actually normally bring significant weight added to the motorcycle. Therefore, there are some other alternative solutions provided, for example, like from Honda or from BMW. Actually, they based on the concept of robotic application, where they try to use some mechanism For example, like Honda, they apply some mechanism to their head body where you can control the weight dynamically and also control the steering to adapt and to make it self-balanced. So similar to the concept of the mass moving, and then they try to use that in order to make it better. The challenge in autonomy with two-wheeler, you can see is linked to the customer acceptance. So normally when you buy the motorcycle, the expectation is to get some degree of freedom in order to try to engage with the vehicle and also try to use your own experience in order to get the best performance you like. However, if you try to make the vehicle to be fully autonomous or at least getting some driving assistance function, that means you try to reduce the level of the freedom when driving the motorcycle. That means when we design the motorcycle, the motorcycle maker needs to consider the trade-off between the customer expectation and also about the safety level. So when they design, the primary goal still will be about safety rather than about autonomy level at the moment. And another challenge given to autonomy in two-wheeler is around complexity and therefore the cost aspect about designing an autonomous vehicle. Another trend in motorcycles will be around connectivity. So the same for four-wheeler with the development of IoT and technology. So definitely we consider or we expect that motorcycle also have some ability for connecting to network as well. So there are about 7 key areas for motorcycle sector need to consider, is including the mobility management, so commerce, vehicle management, safety and breakdown prevention, entertainment, drive assistance, and well-being. So all of these technology nowadays can be considered for a smart motorcycle, and that can be done through a V2X technology. That means you can cover from V2B, V2I, V2C, or V2P, for example. The main challenge when you consider for connectivity actually linked to the safety and reliability of your vehicle. So you need to make sure that your vehicle will be exposed to hacker. Also try to consider about the sensitivity or GDPR, mainly to protect your sensitive information when you drive your vehicle. Another issue is when you connect that vehicle, especially go to the level of autonomy. So you see that the information from here will be synchronized with your vehicle function or driving assistance function. So how can you keep your vehicle reliable will be the key for connectivities in motorcycle. And the last emerging trend for motorcycle, I want to say, is around the mobility as a service. So nowadays we're talking about the inclusive environment where we try to see how to reduce the number of vehicles and also how to improve the access from all different class of people and also from different regions to have the ability to access in transportation. So the idea around the mobility as a service actually mainly covering the car sharing, the scooter sharing or bike sharing, or consider some alternative transport service, ride sharing, on-demand ride service, or the courier network service. So with this type of information, it can offer you the massive impact on many global cities and also enhancing the transportation and inclusive environment. However, the problem with the mobility as a service, quite similar to the connectivity, is around security and reliability. So you need to have a very robust system in order to make sure that you have the secure Hi-Lai service where you need to prevent from loss of your vehicle, and also about operation challenge. When you have that type of security, therefore the complexity in programming and infrastructure also will be another issue for widening the mobility as a service for motorcycle. Okay, so that's the key challenge in developing the future motorcycle. And next, I want to show you, if you want to build that Hi-Lai future motorcycle, you definitely will need to consider about the control system. So here we talk about the electric motorcycle safety critical control development. So maybe some of you already work, or many of you already work on ISO standard for safety in transportation. So what is it, and how can you consider that one in motorcycle development? I will give you a very brief intro today. So why we need to do functional safety? I think the easy answer is in order to make you safe when you drive or driving any vehicle, and also for your family or for your customer or for your passenger as well. So first you need to meet your legal requirement. The second, to follow your best practice. The third one is to definitely avoid damage to your reputation, and more important is about to avoid hurting people, so especially yourself or your customer. So that's the key idea about functional safety when you design the vehicle, and you need to ensure when you build the vehicle control system, you need to satisfy that type of requirement. So I can show you a very simple kind of example. You can see from many resources from internet, we have accidents everywhere, and actually in order to minimize the risk when running the vehicle, we already very familiar with ISO standard 26262, is especially designed for road vehicles. That is the functional safety standard, to make sure that when you design the control system, you need to follow that standard to make sure that the vehicle will be safe when it's on the road. And that type of road vehicle standard ISO 26262 nowadays has been adapted to the motorcycle sector, except the mod version. So ISO 26262 is an international standard for functional safety, and actually is need for to provide the need for design a safety system for electric or electronic system where it's installed in the series production vehicle up to 3.5 ton, and with the latest version of ISO 2018, actually now is already adapted to motorcycle. So the key idea for this standard is to help you with the architecture and functional aspect, to help you to design the aspect including safety life cycle and avoid the systematic fault when and also try to control the random faults when you are running on the road. So with the adaptation of ISO 26262 to the motorcycle sector, so originally they based on automotive safety integrated level, we call ASIL, and they have a 4 level. And then similarly, when we move to motorcycle, when you design the control system for motorcycle, you also need to consider 4 level. A level normally considered as the lowest level, or maybe qualified or quality managed. So in this case, we do not really need about the safety standard to be applied, where level B consider about up to 90% of single point fault or up to 60% latent fault, where level C and D gradually increase the level of safety, also the priorities of the probability of the fault. Like AC level D can go up to 99% of single fault, and also the 99% of latent fault. So the key message here, the higher the ASIL or MSIL, the more effort is required for ensure the safety. So just very to visualize the idea of the safety level, or when you design control system for motorcycle, the picture showing here indicating the ASIL level will be the combination, or the MSIL level will be the similar combination of the probability of the exposure, the controllability, and the severity of failure. So you can see, if you see in this 3-dimensional table, the first one is about the severity. We have from level 1 to level 3, actually that means from the very, very minor injury into very significant injury. And then we consider about the probabilities of exposure, also from very low to high level, and the controllability from very simple or easy to control to difficult or uncontrollable. So you can easily find out that the highest level given to the most significant case where you're unable to control and you face with very significant incident. So that is the way where we design the control system. You need to follow and consider which part of the vehicle will be the critical part causing the significant injury, and you need to design carefully to meet the standard. And on my right hand side, I show you the table of the ISO 26262 when they try to map between the MCU in motorcycle to the ACU in automotive. So when you design or develop any control system, you need to follow that kind of standard. And here is the one example of the self-assured approach from the NXP Freescale with using 4K element. That is the key element using for any vehicle control system development. So we have the safety support on the top, where it starts from the requirement or the documentation, go to the safety design for the hardware and for the software. So as you can see for the left and the right side. And the bottom one for safety process, especially when you go to the testing phase before it can run on the road. So that's really critical when you need to test through many stages in order to confirm your vehicle is safe enough to pass to the end user. So especially if you look into the safety for software development, as you can see on the right hand side, they normally based on AutoSAR platform in order to develop a control system. So what is AutoSAR? AutoSAR actually is the automotive open system architecture, as you can see is demonstrated by this picture. The traditional vehicle software control system design, normally we specifically design for a specific application. That means for a range of motorcycle or vehicle or fleet of vehicle only. When you change any design of your vehicle, actually you need to design or redesign the hardware and software to fit with your application. When you move to AutoSAR standard, there will be the intermediate layer between the application and the hardware. So in this case, even when you change the design in your hardware or in your application, actually you still now can fit to or you can still make it work together because you based on the same common standard from AutoSAR platform. So that's one that has been developed by automobile manufacturer, by supplier and tool developer to make it work. And the key benefit of using AutoSAR is mainly about the flexibility and also the transparency, and it's easy for transfer between partners, between developers, and especially providers. So that means now you can make the whole vehicle based on different like parts or different partners, or based on the full supply chain without making, and also you can make the change in the vehicle without updating the hardware and software design easily. So that is the key aim for AutoSAR application. So when you design the system or control system, you need to follow that standard in order to make it work. I will come back to this one later when we talk about the activities in the WMG. And this is the core architecture when we consider for a control system or software architecture in AutoSAR. Normally we will have a 3-layer in any electronic control unit using AutoSAR platform. The first one we call application layer is normally about control function you want to deploy in your vehicle. The next one is about real-time environment in order to make sure that your vehicle can run in real time using that control function. And the third layer will be the basic software where the information from your application layer will send through the real-time environment and pass to your basic software in order to interact with your actuator, your sensor, and anything else in the vehicle. So so that's now will be designed following this hierarchy. So any developer or supplier, if they are responsible for any part of this diagram, they just need to develop for them following this standard, then they finally can connect together easily. Okay, so that is all around this couple of brief intro around the emerging trend for motorcycle and also about the requirement for software development. Now I would like to show you about what we're doing in WMG at Warwick. So University of Warwick actually located in Coventry in the UK, you can see from here. And we also have a number of research around motorcycle. WMG has been established in 1980, and at the moment, Warwick actually within the top 10 in the UK and about top 80 in the world. In WMG specifically, we have about above 700 staff working in 10 buildings, and actually we engage closely with industry around 1,000 companies so far. And actually we are one of the 7 low carbon mobility center in the UK, mainly focused on that sector, for energy sector. And the main aim for us will be try to consider for technology transfer from academia into manufacturing. So from my team, I'm actually leading the energy management and control system within the energy application group. And for motorcycle research specific, actually we have a number of student projects. We also have a number of projects with the government or with the OEM for developing their motorcycle. So here is one example where we work with BSA Mahindra from India. This is one of our current projects on motorcycle. And we try to build an electric version with the partners in order to make this work and commercialize in the very near future. The key area from our WMG to contribute to motorcycle, including functional safety, vehicle and energy management, vehicle control, about bespoke simulation platform, and also about the engine or energy system characterization and testing. Actually, the topic of battery characterization and testing is from our battery group. Okay, so let's start with each topic. The first one is around the functional safety in software development. So we are involved in we're supporting the partner from the design requirement to safety plan to the safety development during the hazard analysis and also risk assessment before we can consider about safety case and gap analysis in order to help you to build the software. So here is one picture where you can start from the rider to the motorcycle. We're passing through a number of blocks in your vehicle control system, and that's where you need to consider about safety design. So we work with the partner in order to design the functional safety, and you can see from this that color. So WMG contribution will be in the green color or the cyan color. So we involved in the software development in the application layer. We also supporting the development of the functional safety following the AUTOSAR standard, and then it's linked to the verification. So we normally lead the control development in the application layer, and then we build the software with the partners for testing, and we also support the bespoke simulation platform for the verification. So that's the core area we normally support with the software development in WMG, for not only for two-wheeler but also for four-wheeler. And this is one of the example when we build the project for motorcycle. A number of the control feature in the motorcycle we already defined with the partners for the A0 level. So for example, like vehicle supervisory control need to be A0 C level, and also another other control function, for example, like motor controller, the battery management system, or HMI. You can see from this table, that's the level A0 or safety level we need to consider when we design the control system. Going deeper into the control software development, especially for the application layer, we can see that we involved in the system design and sizing. So on this slide actually gives you the idea of how can we support the partners or the OEM in terms of designing the new vehicle. So we can start from the like very simple pre-system design or conceptual design, and then help you with the by providing you a decision-making tool to make the vehicle or to design the component or select the right component for your motorcycle. So here is one example. How can we build that development tool? So we start from the very simple like input or requirement or specification of your motorcycle. If you want to design, you need to know about peak power, the rate power, or the range, or the any other information about power or energy density. From there, we can start with the component sizing using the backward-facing calculation. So you can see this is some very basic example where you do the reverse calculation from the drive cycle back to the energy power and power requirement. It's helping you to identify the component. So with the component sizing, we use backward-facing model. It's mainly like using the expressive version. And you can see from this picture, is the one example of expressive version. When you complete that calculation for siding, then you can start to evaluate the performance. So using the backward-facing calculation with the component feature, and then try to fit this one into forward-facing. So you can start to consider to try to validate your model or your system. After selecting the right component, you can try to validate again if it's work as you expect based on the design requirement or not. And then also you can do some sensitivities analysis to help you with the sizing optimization. So for example, if you try to do with different configuration of your battery, then in this case, with the sensitivity analysis, you can try to identify the optimal design of the battery. Here is one example from our design tool where we try to use the Hi-Lai or the Zero motorcycle, and we try to base on that we use our design tool. So based on the actual commercial motorcycle, the energy consumption will be 85.5 watt hour per kilometer. So with our model, we can estimate the use of that motorcycle around 87.8 watt hours per kilometer. So the accuracy is quite good, where it's about 1.2%. And overall, when we consider for the other drive cycle, like urban range or using highway drive cycle, the highest lowest accuracy actually will be about 5%. That means the tool quite accurate enough for the early design phase, where you consider all the component sizing and also the right component selection. When you have the vehicle design, you can move to a different hardware control and software development. So we're supporting from the vehicle supervisory control level, where you can see from here, we work with the partner, especially for application layer in the AutoSAR architecture, and try to help you with very basic supervisory control before you go into the high level of any advanced control function. So in terms of advanced control function, we have the vehicle dynamic control, and you can see we support with torque management or traction control. We also support with power and energy management. You can see from here, we have the power management and we have a range management. So we can show you some example in the next few slides about different topics. Here is one example of our traction control development. So the key idea about traction control is around try to provide you or try to consider about the drivability when you are on the slippery road. So you can see from the concept of the slip razor relates to the friction coefficient. So as you can see from this diagram, whenever your vehicle passes through the optimal slip razor, for example, in this case of the drive tarmac condition, where you have optimal slip razor, we identify here. So if your vehicle slip is higher than that optimal slip razor, then you will be passing from the stable region into unstable region. And especially when you apply the brake without ABS, you can come easily into the critical case where you can may fall down or your vehicle will have the wheel lock scenario. So in this kind of scenario, we need to consider traction control to regulate the torque or to control the brake in order to minimize or try to prevent your vehicle to come out of the stable region. That means you need to keep your vehicle in this green region. So the challenge for traction control for a motorcycle, we can consider, if you consider the model-free approach design, actually you need to take a lot of training and design effort in order to make it work. Or if you follow the approach like using the model, then therefore the model actually will lack of accuracy, therefore the robustness of the control system will be the key or the main challenge. Another problem with the traction control will be about slip razor. So most of the control system in current state of us is based on the understanding or based on the assumption that you know the driving condition, you know the road condition, you know to identify the optimal slip razor. Or however, in the real life, actually the optimal slip razor will change over time due to the road condition, but also about your bike speed, and also about the change in response as well. So to accommodate with this kind of problem or to overcome this problem, we provide a solution with the advanced traction control using the techniques from command feeder and slide mode control. So this is one example of our design solution for advanced traction control with the two state, with the state of estimation for the torque and slip calculation, and then go to the second state of estimation to consider about the robust control technique to ensure the optimal slip will be matched by the control system. So by doing this, we're regulating the actual control torque going to your motor inverter in order to compensate for the slip happen on your wheel, in order to make sure that your vehicle wheel slip will come to the optimal slip value into the socket period. So here is some simulation result we have from our advanced traction control. You can see from the diagram here, when you have the bike speed and wheel speed, when you have in the slippy condition, in this case we test from snow to wet and ice and back to wet, snow and ice. So in this case we can see with the advanced traction control, we can try to follow as much as possible according to the slippy condition. That can be indicated by the way we track the optimal slip ratio. So with the traditional traction control, actually you just try to assume that you know the slip condition and try to follow that. In this case, we try to make it around 0.5, 0.1, where in our proposed advanced traction control, we can predict the optimal slip ratio based on the actual measurement from the vehicle. Therefore, we can try to make our control system to follow the optimal slip as much as possible. So with the prediction concept, we now can maximize the speed for traveling, and also we can minimize the slip behavior of the vehicle by tracking the optimal condition. By the end, we can ensure that we can improve the traveling distance. So as you can see from here, by increasing the speed where you still can deal with the stability and reliability of your motorcycle, now you can have a longer distance. It has been indicated by this one. So after 1 hour driving, actually you can improve about 12 kilometers in theory. That is the advantage of using advanced traction control proposed by our team. Another one is about range management. So it's very key for when you move to electric motorcycle application. You need to understand about the range of the motorcycle. So we provide the solution for predicting the energy remain in your motorcycle, and therefore to help you with range management. Here is some outline of some of our pilot study when we consider about the range management and prediction. So we coming from the very simple Hi-Lai battery available power prediction, where you consider about how to predict the remaining range in your battery or remaining energy in your battery. And then we go to the driving condition recondition using some Hi-Lai spot vector machine, and we try to identify the driving condition. Thus we help you to identify the right condition you now operating. And then combining with the estimated power or the remaining power in your battery, now you can have a better prediction for your remaining range of the motorcycle. So the pilot study indicate that we can go up to about plus minus 2 kilometer accuracy when you apply the range prediction about or within 160 kilometer travel. Another topic we also consider will be about fast charging. So, especially when you consider for electric vehicle. So fast charging is the key in order to make sure that your vehicle can be refueled in very short period. So we base on two main principles. We base on the first one is a contact relaxation profile. It's mainly used for offline charging profile. So the lithium plating is one problem when you do the fast charging with high current and especially at high temperature, low temperature. So you can see this is some Hi-Lai indication of the voltage in the relaxation phase, when you can see the indication when it changes the slope, you can easily find out the local minimum in this area. That is the indication of lithium plating you can see on the battery cells. So that's we can see from some of our reference in this slide. So with that kind of lithium plating and based on the voltage relaxation profile, you now can derive the charging strategies in order to eliminate that problem. So by tracking the VRT behavior of your battery, you now can derive the right current for charging the battery. So that is the charging procedure when you apply the fast charging from WMG. So we derive the offline profile, and based on the voltage calculation, we can try to update the charging current in the real time in order to make sure that the problem with lithium plating can be minimized. We also provide you the online fast charging protocol, which is based on impedance tracking approach. So that is the concept for impedance tracking. So if you have an ideal battery, normally the impedance will be follow that type ideal curve where you have a high impedance at the low SOC and at the high SOC when it's fully charged. However, when you have the lithium plating into fast charging, in this case, you can have a very abnormal behavior when you changing the slope from positive to negative side. So when you have that type of changing of your impedance, that is the indication of your lithium plating. So by tracking this type of information online, you now can try to avoid the lithium plating by controlling your charging current. That is the concept behind of our fast charging using the impedance tracking. And by combining between offline strategies and the impedance tracking control concept, now we provide you the online fast charging profile by checking the impedance in real time and help you to correct the charging current. So that is some kind of like concept you can find out from some of our publications given in this slide. So our pilot study already proved that by using either the online or offline charging strategies, we can save or we can improve the lifetime of your battery. So if you consider about your first line in the battery, that means you drop 20% SOC. With the online offline profile provided by WMG, you can increase the number of cycles from 80 to 140 or up to 280. And also we have another topic about brake blending or regen braking. Due to the time limit, I just want to give you a very brief introduction. So we combine between fuzzy logic and the nonlinear model brake tape control, when you consider about different factors, not only about regen braking to save the energy during brake, but also we consider about the lifetime of your battery, considering the state of health and considering the temperature of your battery. We also combine with other factors about the efficiency when you consider regen braking. That will help you to improve the ability of regen braking during braking function, and but also you can improve the lifetime of your battery. So that is some pilot study has been carried out, and you can see that it compared to the basic rule-based control brake blending strategies with our optimal brake blending strategies. We can improve significantly amount of regen braking while we still can maintain the temperature and maintain the battery instead of just in the optimal range. And the last one is about our simulation platform. We also provide you the real-time simulation platform for motorcycle development. This is just some picture of our platform has been used for different projects. As you can see, we can come from very simple like model in the loop simulation to the hardware in the loop simulation. And that is some like picture of our fabric we use for motorcycle development. And also we consider that one for 3D simulation when we combine with the IPG motorcycle maker. So you now can test the controller in the real-time environment in 3D. So that will help you to confirm your vehicle is safe enough before running into the real vehicle when you apply it to the prototype. Okay, so that is the all of our activity in WMG. Hopefully can give you some idea about our research linked to motorcycle. Going further in the future, we also consider for the vehicle design improvement, modeling simulation improvement, especially for the rider model, considering the AI and machine learning with human factor to give very comprehensive rider model. Or going further with the control management, we also hope to improve our control function to make it more generalized application, and also try to make it more adapt to the new variants of motorcycle. That means the predictability and adaptability of our control function needs to be improved. At the end, I hope to spend 1 minute to give you one idea of our success story on an electric motorcycle application, and we already worked successfully with our partner. That is one of our projects released last few months. That is the work we do with Triumph. So that is the T1 project we have done. Thank you for your attention. For further information about this T1 project, you can find easily from YouTube. There are lots of videos, including WMG instruction about this project. Thank you.
Okay, thank you. Thank you for your nice presentation. Any quick question? We are running out of time, please.
Hello, good morning, Frank. It's me, Adolfo Silver. Thank you for your nice keynote speech with such a very interesting analysis of the transition of motorbike from internal combustion engines to electric motor. In your opinion, this is my question, in which way the transition to electrification could contribute to the increase of safety about riding of the vehicle? You also showed something about traction control, the regenerative braking with control of sleep. But in your opinion, which are the challenges that the opportunity of transition to a greener vehicle with zero local pollution could also contribute to the increase of riding safety for such a new generation vehicle?
Thank you, Arnulfo. I'm not really sure if I can hit correctly because there are lots of echo when I listen to your question, but I think your question is around when I design the traction control and also regenerative braking, how can I ensure the safety when you design this system? Am I right?
Yeah.
Thank you. So yes, so the purpose of designing the traction control is already to improve the safety feature. That is the primary role when you design the traction control. So when you try to bring your vehicle, try to minimize the slip. That means try to make it match to the optimal slip ratio. That is the way you try to improve the safety and reliability. However, as I mentioned, we involved in the development that is only for the implementation in the application layer. If you want to deploy this kind of technology into motorcycle when you go to production, you need to consider for the safety feature. That means you need to design, after passing to your application layer, now you need to involve with the other safety function in your motorcycle. So when it's passed to the vehicle, so when you make the decision with traction control, for example, that is not the final decision to go to your motor inverter. It needs to pass through the other safety feature before you can have the final decision. So all of the safety features need to be considered separately, not within the traction control, but will be will be in the series before it's sent to the motor inverter. So yes, the traction control and regen braking as in the application layer and link to the vehicle. We go pass through the AutoSAR platform, and then from there you need to consider if you say designing the motor, say for the motor controller, then you need to consider for ACU, for example, level C. When in there you have a different scenario for this for safety, and then you need to make sure that it's passed through all the safety check before it's sent to the motor input.
Perfect. Thank you so much.
Thank you.
Okay. Any more questions? All right. Professor Dean, thanks for your nice presentation. This gives us a lot of information about the new trend or the electrical motorcycle. Thank you very much. Thank you.
Thank you very much. Thank you.
So I want to end up with this keynote speech. And then the next keynote speech will start at 15 minutes. Thank you.
Now we have the break outside the room. Please enjoy.
Yeah, it's okay. So, でもこれ13分じゃない。Yeah, yeah. And but
So the laser point
The building type of laser with light point.
because the screen is on here.
Again, online user have to be watched over the
yeah. So if we use the laser point here,
they can see.
yes, cannot see.
So maybe the function of PowerPoint. Maybe this arrow mark will change like this. Is there any option to the PowerPoint? Mouse? これがない。あ、これがこれだけ。グリグリがない。
そう。もうだから、ゴーイさんが出る。だから、
じゃあダメです。
まあどうかな。
じゃあなしです。
そう。
マウスオートもやったりする。Actually, the PowerPoint has that kind of option, but you have to hunt the mouse in. Otherwise, you can use a laser pointer online. Yeah, these are.
Can I use this?
Yes. And when you then when your presentation of the if you use mouse, you can use it. Sorry.
The presentation is finished and ask a question for the audience here. It's okay, but for the online audience, please pay some attention about that. Or you notice me that there's a online audience.
If the other audience has a question,
So, please go.
刚刚是有是那个就是抛空的那个开盘，可是这样的话就是毛主要就让演讲都还是开个不要。还是他是不是他有想要看配偶？因为这样他这个就的话，比较这样多。没有就是请他看他就是他的电脑开出方面，然后就像他那样分享给我，只是他们在实际就是现场开出工艺这边。Maybe we can use your computer and use Google Meet like yeah. It's a
Yeah, no. It's not to use this. No. Thank you.
Okay, so here comes the time to start. Good morning, everyone. My name is Nov.20 from the Kaohsiung Prestige Japan. I'm a chair of this keynote session. I'd like to, at first, I'd like to introduce the lecturer of this keynote. Professor Hayato Yoshioka. Dr. Hayato Yoshioka is a professor at the Institute of Industrial Science, the University of Tokyo. Professor Yoshioka obtained a degree of Doctor Engineering in Mechanical Engineering from the Tokyo Institute of Technology. His research is the development of ultra-precision machinery technology for manufacturing system. He has developed several ultra-precision mechanical technologies such as questioning table systems, spindle systems, and process monitoring systems. And recently, he has been interested in the realization of the flexible manufacturing system with industrial robots. The number of JSME, JSP, JSA, USPEN, and CIMT. So, if you are ready, okay. So, please start the keynote session.
Okay. Thank you, Professor Sakawa. Good introduction. Good morning, everyone. Maybe good afternoon or good evening, online audience. Today, I would like to talk about advanced manufacturing system based on mechanical mechatronics technology. So, sorry, wait a moment. Something wrong. Okay. Wait. Thank you. Okay, so this is my agenda. Let me first I explain the introduction and background. And today I prepared two topics. One is mechatronics in precision machine tool, and the other is mechatronics in manufacturing system. So finally, I would like to summarize my presentation. Okay, I have this question because the professors are already me. And then, to be honest, my first presentation in international conference was ICMT 2002. It was in Kaohsiung, Japan. So this presentation is very honor to me. This presentation was very important and impressive for me in my career. So, okay, this is the introduction. So, this is the population of the world. Here is the year and the population. Now we are here, 2020, almost 8 billion people. But 40 years ago, when I was born, and 1980, the 4.5 billion, but 40 years after, over 10 billion people. So, and the right period shows the population growth rate. The blue means decrease country. So the number of population increasing, but some area or some countries population decrease, especially in the developed country, developed area decrease the number of population. So, and the social issue are rapidly changing. So, as you know, the SDGs, sustainable goals, are very important for us, and the carbon neutrality or green transformation. And as you know, this month we have the COP27, and so industry or industry sectors have to change in quality and quantity in both sides. We have to solve the some social issue by some technical or engineering technologies. So this is very famous proposal from Germany, Industry 4.0, that was proposed almost 10 years ago, and they call this the fourth revolution, fourth industrial revolution, by using some informative technologies like that. And on these concepts, these digital, various digital model proposed, the data twin or data shadow, CPS, so many digital technologies applied to the manufacturing field. And left here shows the relationship between productivity and flexibility. That is a very common relationship. If we want to produce the mass volume of the product, we have to design the FDR in the special purpose product line, but it has low productivity. So if we want to high productivity, the amount of production volume decrease. It's a very common relationship. But now that this is the relationship or transition of the manufacturing paradigm or manufacturing system paradigm. Here is the 90s centuries, and it began to modernized or some using robotized. And now we are here, and it is the fourth version of the industrial field. And this is the culture in the manufacturing field changing and transition to the return here. So it means that several volume that we must produce the various kind of products. There was customized or personalized, the very wide variety and mass production in the mass customization. So today I introduce our group research, made two topics. One is the fast-to-south system for milling process, and the other is a flexible machining manufacturing system with an autonomous mobile robot. And this is the technology for one machine tools, and right finish the for the whole manufacturing system. So first, I introduce the first two salon, and this is some example of the functional surface in industrial some product. This is the workability or optical some surface. It has a very micro texture on the surface to get to realize some special function. So when fabricate these micro patterns, it is suitable to apply the MEMS process normally, but these 3D shape, like a curved surface, it is very difficult to apply MEMS technology. So we have to use some mechanical process. So, but the mechanical process takes so many time, too long machining time for fabrication of these fine patterns. So the shortening machining time by using fast-to-servo technology. The fast-to-servo is the local driving system of tool, cutting tool. So in that case, usually the piezoelectric actuator is used as a local actuator, but it needs wiring to apply the high voltage. So it is difficult to apply milling process to the rotational tool. So we use the giant magnet selective actuator to position the tool, because the giant magnetic actuator can drive by the magnetic field. So it means we can drive the actuator in non-contact function, so it can rotate. So this is just a simple concept figure. Here, yellow part is a GMA, giant magnetic actuator, and that is rotate. So the cutting tool is located here, and this is a tool holder. And we set the driving coil at the stationary part. So if we apply the current to the coil, the generated magnetic flux conduct here through the magnetic material. So the tool can be driven by applying the current to the coil in non-contact function. So if we can realize this pass-through servo technology for milling process, it is very useful to fabricate fine and precise pattern on workpiece surface like that. This is the home machine. This is the machine tool, and the spindle head is driven or fed by the normal or feed axis, and this quick and fine local motion is synchronized to the motion of the feeding axis, so we can generate the form geometry and fine patterns simultaneously. Yes, that is the conceptual figure. Here that is the GMA, and the long range linear position platform. Platform is the feeding axis, and plus GMA motion in local motion, so it can generate this pattern curved surface. So it is very high efficiency micro patterning on curved surface. This is a prototype we developed. That is basically horizontal 3-axis machine center. Here is a workpiece, and here is a spindle, air-set spindle. And the workpiece is fed by the X and Y linear motion drive, and the spindle is driven by a Z axis. So it can generate 3-dimensional motion. And sorry, we cannot see the tool, but this unit is a pass-through servo unit for milling process, and with a driven coil inside. And this is a driving unit of for pass-through servo with GMA, and here is a GMA actuator, and this is made of PEEK. PEEK is one of engineering plastic, and here is a magnetic material. Here, sorry, the two magnetic material discs sandwich to the GMA, and this is a correct jack to hold the rotational end mill. And this is a schematic diagram of the unit. Here's a driving unit, and these are driving coil, and of course the driving coil generates a large amount of heat during driving, so we need some cooling system. Integrate water jacket we used, and GMA is a very large, has a very large hysteresis, non-linear characteristics. So to compensate that, we installed the positioning sensor, displacement sensor, like that. It's a beam-shaped capacitive type sensor was installed near the cutting tool to eliminate the effect of tilting, the error parameter during the position. Yes, this is a appearance of the error system. Here is a first to subsystem, it's cooling. Here's a workpiece. So the positioning resolution of each axis 1 micrometer, and the rotational maximum rotation speed is 20,000 RPM. Yeah. So first we evaluate the frequency response of the developed system using the Swift sinusoidal signal. And here is a board diagram of the system. The gain decrease at over 300, 140, around 400 out. Here's the bandwidth. So this is a very not extreme fast, but it's much faster than normal feeding axis or the axis. So it can generate the very quick motion, quick fine motion during the machining. And next, we evaluate the positioning resolution of the first to third system. The left figure shows the stepwise response with 0.1 micrometer, 100 nanometer stepwise in non-rotation condition. So we can see clear stepwise response of the tool, but during the rotation, 10,000 RPM, we can see very noisy response. I'm not sure the reason of this response, which noise from the motor or some rotational the error of parallelism of the capacitance sensor, but we cannot achieve the same level of the position resolution, but it can realize less than 0.3 or 0.2 micrometer position resolution during the rotation. And this is some simple cutting test using this system. And here's a workpiece, and we apply the initial vessel cut of 10 micrometer here, and the feed by x-axis, just straight motion. And during the feeding motion, we apply some stepwise additional vessel cut by FPS. And so 3 micrometer, 5 micrometer, 6 micrometer. So here is a measured workpiece, machine workpiece, and to determine the step height from the result. The 3 to 1, that is very low machine error can be achieved. So in this not so heavy cutting, it's a very precise cutting, so it can, this developed system can be applied to the fine machine. And the next is the generation of micro pattern curved surface. This is a two-field motion by 3 stages, and we addition these first to third motion like that. So on the workpiece surface, these the resultant trajectory by these motion copied on the surface like that. And so the first two servo reference is 10 Hertz. It means 10 dimple per second during the field motion. And this is a microscope image of machine surface. We can see small dimple is arranged like a grid here, and this is a 3D shape of the machine surface, and it's a cross section of the dimple. So we can see clearly dimples aligned in constant pitch like that. So it can, the developed system can generate these micro pattern curved surface. And this is the measured depth of each dimple. And yeah, in Y-direction, using this measurement result, it's a 9 dimple. We want to apply the 5 micrometer reference depth, but sometimes it is short to the reference depth. And the average of the depth 4.8 micrometer. So we check this dimple precisely. So we can see some small bump at the center of the dimple. So it means that it means the center of end ball end here. So there is a small gap at the center of micro end here. Okay, so let's go to the next topic, the manufacturing systems mounts. Yes, this is a mass production line. It's a very famous picture. It's the very famous automobile, the Ford Model T, and it was produced by this production system. It's a job shop, right? It's the workers bring every part, assembly parts to the body and assembly. But after that, the maker construct the belt conveyor line to control the rate of production. Of course, nowadays we replace workers to the industrial robot. But of course, these robots are fixed on the floor of the factory, so difficult to change the layout. So the flexibility of production is not so high. So this is a collaborative research with machine to build. It's a Machinum milling machine, and they propose this new concept production style. here is a assembly machine tools body, and they produce the handling of the assembly parts and industrial robot. All of them delivered by the AGV or self-mobile robot. So the workpiece in that case is structural body, and to move freely, it makes it realize very high flexible production style. And that is a concept video by Makino. So there's some AGV, AMR, and automobile robot. It's not a machine line, it's an assembly line. So here is a version of belt conveyor line, and this robot can move freely. Yeah, and when I heard this concept, I think that it's very difficult to realize these technologies. Yeah, that is concept. So their concept is here. Is the machine tool customers want to not use normal regular model, and they want to customize so many tools or using robot to load or unload. So many customize. So the productivity is quite changed day by day. So this is operation 1, 2, 3, 4. It's a operation. Here is a bottleneck in the product line. So they use they move these robots or some instruments to cover the productivity. So maximize the throughput. So they dynamically change the production line. So that is a function referred to for alien house. So I skipped this slide, and then we developed 3 types of alien house. Just a simple one is a mobile robot to deliver some parts, and this is a AGV with some lift up functions, and here is a mobile robot with some industrial manipulator. And this AGV uses not normal tire. They use the mechanical system to move on direction. The tire has some rollers around 45 degrees tilted, and the combination of wheel rotation determines the moving direction like that. So it can realize this flexible motion like that. And the video is maybe faster than the normal speed. Yeah, like that. If we use something strange motion, and the white one is a normal strange system, it is very difficult to through the corner. And of course, they developed the large size to large size AMRs to bring the heavy parts. The 5,000 payload, and of course that is very large robotic arms installed on the HPs. And this is the position control of the AMRs. AMR is controlled by the SRAM usually, but it is difficult to achieve high precision motion. So we switch the control method nearby the local boards. We switch the grid map by LiDAR to the point cloud data near the goal destination. That is a result. It's a normal mode with causes 330 or 40 millimeter error, but the new control method is less than 10 millimeter. So this is a developed prototype line of that in the laboratory. So here's a assembly tools, and here's a mobile robot. Yeah, of course. These robots are fixed on the floor to lift up the very heavy assembly parts. But other robots are free from the floor. And this is just a pilot prototype line. But, and to assemble the ball screw on the machine tools. The medium motion die and tighten the bolt automatically. But we need some change in design to make the assembly, easy. It's suitable for the robot assembly. Next station. The conglomerate of two industrial robots. The heavy part is taken out. And fix them. And this is the assembling of sound motor. So sound motor is too heavy for human operator usually. So, but the robot can lift up easily. Okay. So, and next is another ongoing project by using AMR. That is not mapping project. That is this consortium project. Mori and Pan is a very famous machine builder in Japan, and 4 universities, Kyoto University, Keio University, the University of Tokyo, and Tokyo Institute of Technology. We try to develop or realize the dynamic production line with a multi-function mobile robot. It means this is a present or conventional production line. Is a product A or B. It's made each line, and the line has some machine tools or something instrument, and the human operators check for operation, evaluation, operation to the each machine. There are skilled operators cover machines. We want to replace these operators to the mobile robot, and so this is a mobile robot by Mori, and it makes observation or evaluation of process, and of course its data, the monitoring process on the machine data is uploaded to the cloud or by HANA, and this concept, and if some machines are broken, so usually the product A cannot produce ever. So, but this AGV or AMR can deliver or move the workpiece to another line like that. So we can continue the production of both A and B products by using these systems. And but this is not this project. That is introduction of this AMR robot by Mori. Usually, this type of machine is used for loading or unloading of workpiece or tools. But we try to realize some inspection or measurement or monitoring of the process. Okay, you can see this video on YouTube. This operator is standing, so you can take another pass. So this is just the going project. So this is our research group topic. Is that the AMR with 3D scanner we developed, and the measurement of workpiece on the machine tool, or it comparison with the CAD data, so it's aligned on the table system of the in one is compensate the around error of one piece. So that is great. Both type of the system is just a simple rate and here is measuring result. You can get 3D geometry of Mach-3 by this system. So summary. So requests for industries have been complicated due to new social issues, and Mechatronics technology can help to meet these requirements. So one topic is first to south system for milling process to this, and the other topic is a flexible machine manufacturing system with autonomous mobile robot. So this financial support from this organization. So thank you so much for your kind attention.
Okay, thank you very much for the presentation. Is there any question or comment? Okay.
Thank you so much for your nice presentation. It's so nice to see that. So is this part of the university, the things you were showing, the robots? Is that like a lab? All the things that you were showing there? The prototype.
This robot is, we don't have this robot that is in machine to build machines. So we can not have this large space.
Yeah, that's
so,
what I was
yeah.
My question was just about your first section. So when you did the curved surface and measured on it, I'm not sure I understood exactly how did you do the path planning? Is that the path file like this, or is it like some kind of sensing? It sends the surface first and then it does the milling? How do you do it? So for example, if I give you an object, you don't have the CAD file, for example, another curved shape, will you be able to do this on it?
No, just sorry, with the first step. So we define this geometry, each geometry directly.
So you are milling it yourself, the surface, and then so you remove that part. Okay.
No, but for me, generating shape and micro pattern simultaneously.
Oh, I see.
Generating.
Yeah, because I was working with composites, and I was using a collaborative robot for non-destructive testing. So the problem is in the composite is that the shape changes after manufacturing because of warpage. So the carbon fiber and the plastic, they don't have the same shape as the mold. So I was struggling to have the surface exactly parallel to the curved shape. So I was wondering if there was something we can discuss later. Thank you.
Okay. Thank you. Any other comment or question?
I think it's a very interesting research. I'm curious about the first topic about microstructure. In your illustration, it means you say that microstructure can provide a waterproof. Yeah. Sorry about that. I'm not familiar with the microstructure. Are there other applications about the microstructure that we can? Is there another interesting topic about the microstructure you can share with us? when you apply this technology, you can the part can have some mechanic.
Yeah. To be honest, our first target is mode, 3D mode, and to control the surface characteristics to remove or copy and some texture surface. So it's just the image of the functional surface. So to achieve this kind of characteristics, I think the micro pattern should be more small or smaller than micrometer. So it is very difficult to machine by these developed system, I think. Yeah.
I think so. And I have another question is about a control system. Is this a closed loop control system or?
Yes.
Yes. So you have to design a controller to make this precision about 1 micrometer per step per resolution. Do you need to design a controller to achieve this?
Yeah, but we don't use very special controllers. Just use I think PID or as a very common controller.
So do you have a sensor to detect the displacement of your system?
Yes. Main motion of the axis is that is an encoder, and the resolution of 1 micrometer, and the fine motion of tool is capacitive type displacement sensor.
Okay.
That's used for control.
Thanks.
Okay, so yes, the time is running out. So we will have to express that. Thank you for that by talking. Okay, thank you. So I will move to the next presentation. Please wait.
Now is for the speech section part. Welcome to this section for keynote speech part. In this section, we are very pleased to invite Professor Nov.20 to give the keynote speech. Professor Tai received the PhD degree from the Penn State University. Professor Tai has cooperated with more than 25 machine tool manufacturers and worked for over 60 research projects to help the machine tool manufacturer to develop various technologies such as intelligent servo tuning, CNC cloud, virtual simulation and electrical computing. Professor Tai received many awards, including the Industry Academic Contribution Award from the Machinery Industry Association, the Outstanding Engineering Professor Award from the Chinese Society of Engineering, and the CSOE, and received the Outstanding Research Award from the Ministry of Science and Technology. Okay, the speech title given by Professor Tai is From AR/VR Digital Print and AI to the Industry Metaverse. Now,
Let's welcome Professor Hi to give his speech. Welcome.
Good morning. Thank you for coming, and thank you for Professor Zhou's introduction. The topic of my presentation is mainly on maybe it's the topic of this presentation is so-called it's industrial metaverse. This is a hot topic, but somehow it is bad. In order to introduce the concept of so-called industrial metaverse, let me show a video.
If you make anything or you move anything, you create a carbon footprint. If we can simulate that infinitely in the cloud, we can make and distribute that product more effectively, efficiently, and sustainably.
Our supply chain is still very physical. But there is a digital part with the digital twin. We see how to optimize energy consumption, which also translated to the sustainability.
If you think about designing a car, we have thousands upon thousands of decisions to make. How can we be as efficient as possible in making those decisions and give the design team room for the most creativity possible?
Digital twins allow us to optimize value, optimize margins, but also reduce emissions. This is where I think the power of our partnership really lies.
完全なるメタバースの世界は開発から設計ないしは試験までの全ての工程っていうものを仮想環境上で実行できます。
We are working really hard connecting all these bakeries, production lines, our logistics, transportation to provide visibility, traceability, and to be more efficient in the use of water, energy from waste on every bakery.
Okay, actually in this video you can see some keywords. In this video you can see some keywords. One of the keywords is so-called digital twin. Another keyword is like mixed reality, that's MR, and energy management and the carbon emission control. All these will be combined together to form the technology core of industrial metaverse. So what is really an industrial metaverse? Everyone has different explanation or definition on this. And for the international company, one of the famous companies is Siemens. We try to use this kind of concept to do some of the manufacturing process. And the other one is Airbus. The Airbus uses this kind of concept for airplane maintenance or diagnosis. And BMW is really for the supply chain and the factory integration. So what are the core of this industrial metaverse? So if you look at the core of the metaverse, it consists of 7 layers. The first layer is so-called infrastructure. It consists by this kind of 5G, 6G, Wi-Fi. The second one is the human interface. It consists of smartwatch, smart glasses, wearable devices. One of the important parts is so-called decentralization control, which is that not everything you need to use the cloud computing, but you have this kind of decentralized edge computing and AI agents. In order to apply this, somehow you need to have a lightweight AI model. That's one of the topics that I will talk later. And then you have a spatial computing. You have AR, VR, XR, and the geospatial mapping and multitasking. the 5th layer, 6th layer, and the 7th layer is all related to applications. So look at this kind of 7th layer, then what is the technology inside? So the next slide is show you that technology roadmap. As you can see that the communication and computer infrastructure is on the bottom. On top of it, you will see the measurement technology. You will see the virtual reality, connection, and the convergence. And all these are well known in the media, but how can you get all of them together to form the industrial metaverse? So what is to do is that there is open issue that we haven't done right now in order to build up this kind of virtual reality world. So one of the open issues is interactive problem. Once you wear the smart glasses, sometimes you feel dizzy, and you need to spend like 4,000 US dollars to buy a HoloLens. It's not affordable for any person, and you need to have a better interactive devices to immerse yourself into that virtual world. The second one is a computational issue. It's always an issue, no matter how the big progress from before to now. Because if you want to have this kind of totally underlay and you want to create a virtual image in front of you, you need to have more computational issue. The next one is probably the most important one. The most important one is standard and the comparability. So for comparability, if you think about comparability, you think about two companies. One is Microsoft, one is NVIDIA. The Microsoft, you know, they propose a so-called universal theme description language to describe how to connect the metaverse with the real world. And NVIDIA support another standard which is called digital twin description language. So if you think about that, you have two products from two different companies, and you cannot communicate with each other, then you are only confined to one company. So you will not be spread over the world. Then once you connect the world and yourself together, you have this kind of security problem and privacy problem. So what is the metaverse? Actually, it consists of the first part is AR, VR, MR. That means you want to interact the real world with your virtual world. The second one is so-called the digital twin. Digital twin, everybody has different kind of explanation for digital twin. Later on, I will use one of the typical example in our lab to explain what is the digital twin in machine tool. The second, the one that I circle is the interface. That's still an open issue. That means the interface is that if you want to go from this metaverse to another metaspace, and you want to connect one metaspace with the real world, is there any kind of standard that we can communicate with each other? So if you look at this kind of problem, it will come out that the metaverse is a big concept, so we should nail down this kind of configurations. There are four major applications. One is for healthcare. One is for gaming. Gaming is probably the most progress in metaverse, but there's still one for the smart city. The one we are talking about is the metaverse for manufacturing. The objective of this kind of metaverse is somehow very similar to Industry 4.0, that which can shorten the product life. It has a fault detection. It has manufacturing scalability. One keyword is make to order. If you order something, you can definitely know the exact receipt time, and you can know exact the product quality. So you have this kind of make to order manufacturing enterprise. And you have virtual reality for operating transparency. That means you can see your product go through the factory and you will ensure that your product will be in your hand in time. So this is another one that I add in the paper is so-called people training. So if you classify into more specific area, you can see that the objective of industrial metaverse can be divided by several parts, the 5 parts, while the human. So what the human do for the industrial metaverse? Think about one day that you don't need to sit around here, but you are in US or you are in Europe, but it completely like you are in this space. So you can learn how to operate the machine in a virtual world, entirely like you are in the factory. So for the machine, you can think about that you can start from the design and the parameter optimization to global remote maintenance to manufacturing optimization for the machine. For the factory, you can have a process management, or the most important thing is that you know exactly your energy, your carbon emission. For the product, you have this kind of thought. You have a virtual design, and you have a human machine co-work platform. We are thinking about what the next step, how to make man and the human and the machine co-work on a platform, not in real world, but in virtual world. That is so-called the human-machine co-work platform. So for the enterprise, the most important thing is probably the supply chain, MES, ERP, PLM. So if you know about the objective of industry, what is the insight? The first one is everybody know about the AR, VR, and the XR. So can you tell the differences for the 4R? And what is the ultimate solution for XR? All day the not up. So for augmented reality, it's like it's like Pokemon. You go out to the tree, you can project your virtual world into the tree, and you can capture the Pokemon. It's like it's an augmented reality. It's AR. Then you have virtual reality that you complete into a virtual world, and you like playing game with each other. And the mixed reality is somehow like the Airbus maintenance system. That you stand on one Airbus, on top of it you can see all the instructions to see where you can open the field and where you can put the screw on it. And once you put the screw on top, you can see the value of your tension. So in terms of all this one, what is your imagination for XR? That is, you have a very data exchange between your real world and your virtual things. That means once you do something, the virtual world will detect your eyes is going on there, or your motion is like doing like this. The virtual world notice that and they change the thing. It's not completely developed, but it's a trend for the virtual reality. So the next one is that AI. We talk about 3 different components. One is AR, VR, the other one is AI, the other one, the final one is digital twin. We will explain how to implement the AI and with digital twin. So in terms of AI related, you have this kind of feature extraction, you have classification, you have regression, you have segmentation, you have optimization. What is the next? If you want to apply all this AI algorithm into a real factory, what will you encounter? The first one is that when you train a model, and after 6 years, after 6 months, after 1 year, the model loses their accuracy. What can you do? the data you collect during your train your AI model probably is very versatile. You can define any kind of machining condition, but in real application, there is no way that you can collect such kind of big data. Then what are you going to do? Some supervised learning that you require you to label your default or your defect. On the plane, on the factory, maybe you don't have this kind of trainee to help you to label the defect. So it comes to two important technology, which is called transfer learning. How to use less data to do some of the AI application. The other one is so-called autonomous learning. That means you don't need to label any kind of defect. You still can do the autonomous learning. So if you go this and you all related all these AI topic, all the blue mark are the techniques we use in our lab. So if you put all these techniques into a machine tool, you will see that you have this kind of AI machining, AI control, AI manufacturing, AI inspection, and AI maintenance. So once you put all these into the machine tool, you will see that what is the most important thing you want to apply. So the next one is that I just see that the resolution of this projector is very good. Yesterday I'm afraid that you cannot see the picture clearly. You can see that is two of the workpiece that normally encounter when you do machining. On the left hand side, you can see that there is a lot of waveform on top of the workpiece. This is generally caused by vibration. You can see that there is what we call quadrature protrusion on top of the semicircle. This is caused by friction and backlash. On the right hand side, that you can see this kind of, we call it an undercut. So once you see this kind of workpiece, what kind of question you will raise? The first one is that how can you classify this cutting mark? How many cutting marks you will encounter when you do the machining? The second one is how can you locate this cutting mark? If your company has a master technician, probably they will use their eyes. They will use eyes and rotate in different angles to see different kind of cutting mark and tell the operator say, okay, slow down your fill rate. Probably your cutting depth should be smaller, something like that. But it's like a master experience. No way that you will always use man's eyes to spot your cutting defect. The most difficult thing is how to determine the cause of the cutting mark. If you know the cause of the cutting mark, then you will propose a method to solve this problem. So in order to do that, the first question is that how to classify the cutting mark? You require domain knowledge. So if you perform a lot of this kind of working piece cutting on different kind of machine, you can classify into 6 different types. One is speed. If you go up the ramp, there will be acceleration and deceleration. That's something like you have this kind of speed problem. And if you have a plane, but you have a slow slope surface, you have this kind of loading. You have undercut, you have this kind, the whole plane, but you have this kind of hairline, you have vibration, you have quadrature protrusion. So the first one is that you need to know the domain knowledge about the cutting mark. The second one is that how to locate the cutting mark. In order to do that, in our lab, we designed a 5-axis insertion platform that will simulate the master technician, and it will rotate and put on different angle. At different angle, you can take a picture and to identify all of the cutting mark incurred on that workpiece. And we will show the video at the end of this speech to show the operation. So once you take the picture and what kind of algorithm you should apply to identify all these cutting marks. Here we use MES-RCNN. MES-RCNN is generally used for auto assistant driving product defect inspection. Generally consists of 2 stages. The first stage is that you have a backbone network. From the backbone network, you have a feature map. Then you have a region proposing network to identify the location of your defect. After you find the interest feature, then you put a full connecting network to classify what kind of defect. So the finally, you will have a score, class, bounding blocks, and a mask on top of this kind of workpiece. So after you identify this defect, what is the next? The next one is that you want to determine the cause of the defect. So in order to do that, you need to accumulate data. The defect is on the space domain. But in order to decipher the cause of the defect, you need to go back to the time domain. In the time domain, you can measure the vibration, you can measure the encoder output, you can measure the spindle current, you can measure different kind of things. The most importantly, you need to know what is the cause of the result. You need to separate the signal into different domains. What means you need to separate into different domains? You can see from this page. In this page, it's like if you're a mechanical engineering student, you will see that you cover the whole domain knowledge in the mechanical class. The first one, you need to know about the chem. If you set the tolerance too high, you will have what kind of behavior. If you didn't set up the CNC interpolation right, what kind of behavior you will get. If you didn't set up the servo control parameter correctly, what kind of behavior you will have. So you will have CAD-CAM, CNC interpolation, servo control, structural dynamics, thermodynamics, cutting dynamics, spindle and balance. All this together, you will know what is the real cause. For example, you can have a CAM, you output the AC code, you can generate a virtual workpiece. Then after that, if you can measure or you can decipher the interpolation output, you can use the interpolation point to create another virtual diagram of this workpiece. If you have the servo control signal, you can generate another figures of the virtual workpiece. So for all of these together, you can know exactly that which part will cause your defect. But the problem is that you need to combine all these domain lines together. In this case, one of the most difficult part is thermodynamics. So I will see that we would like to use the AI model to predict the thermodynamics, and then the prediction can integrate with the physical-based model. So that's a very good example that some of the model is not accurate to use the physical model, then you can use AI model to assist you for this kind of prediction. So the first one is so-called CNC interpolation. That means that if you want to move this trajectory, you need to know that at this corner, you need to, make your free rate smaller. So the free rate in the NC program is artificial. The real free rate really depends on the kernel of the CNC. We worked for 22 years to work out the CNC kernel for different kinds of commercialized CNC controller. So this is the so-called long segment, and we can get exactly the same as the commercialized controller. This one is shown that we still can deal with the short line segment integration. Long segment and the short segment, that's totally different story. The next one is that you need to develop a servo dynamics model. Once you consider a servo dynamics model, you need to know the drive. The servo drive generally consists of current loop, velocity loop, and the precision loop, and the feed forward. So if you have this kind of model, you can predict that the friction, here there is the model for the friction and backlash. So if you have this model, you can predict that the quadrature protrusion occur in your workpiece. And later on, you can use this model to optimize the parameter to compensate this kind of friction. So in order to do the adjustment, you need to know exactly the parameter in the CNC controller. This is one of the simulations in our lab why we use the circle. Because generally the quadrature protrusion is a curve in this, and the backlash normally a curve at this area. This is the free rate change their direction. So if you can simulate exactly the same, like less than 0.5 micrometer, that means you catch the friction behavior quite accurate. Then you need to have the structural dynamics. That is, you don't treat the free rate drive as a rigid body. You need to use the LSK system to simulate the transmission system, and you can get the vibration when you move, and you can see that after, when you are decay. Furthermore, you can define the elastic elongation during the motion. So the next one is what? Thermal. For me, thermodynamics is the most important part because you didn't really know that the heat source, and you didn't know the environment. So you have a very accurate thermodynamics model, but you change your environmental temperature, the model might not be accurate. So we decided that we want to incorporate the model with the AI model. With the AI model, you can measure the temperature online and use that temperature to predict the elongation of the tool center point. So we use STM to do this kind of prediction. Then this one is so-called the cutting dynamics. The cutting dynamics, the most important one for the cutting dynamics is to online identify the cutting coefficient, and we have this kind of technology to measure the spindle current and the servo drive current to recompensate this kind of cutting coefficient. And this is the result that we use for our simulation. So with all these techniques together and the AI modeling, then you can go back and to find out that where is your cutting mark, and then the cutting mark occur really come from which part? Is the structural dynamics part, thermodynamics part, or integration part, or it just originate from your technical system. So if you have this kind of problem, then you can do the optimization. Optimization is that for machine tool, generally you have three purposes. One is high precision, high speed, high surface quality. So if you could have this kind of index, you can put your model as the best model and use different weighting and the genetic algorithm or PSO to find the base of the integration parameter. All of these constraints is generally used for CNC controller. One is the acceleration, one is related to jerk, one is related to the time after iteration, one is the corner velocity, one is the feed rate. By setting up this constraint, you can get this kind of result. If you want to have a rough cutting, you can use speed priority, and you will choose a technical parameter setting. If you want to have accurate priority, you can have high speed and high acceleration and jerk. If you want to have a surface quality, probably your corner velocity should be small. Something like that. If you get this result, you need to have the capability to judge whether it drops into the local minimum. So domain knowledge in terms of all this optimization is very important. You cannot get a parameter which is not explainable. So that explainable AI normally occurs here. So this is the one that we use in our lab. We can see that from the simulation that you can see this is the one that for backlash. And this is the one for virtual CPS. This is one after optimization. Before you do the cutting, you can simulate the cutting wave. This is the wave due to the vibration. So after you find the optimal integration parameter, you can see that from virtual CPS, the vibration wave is gone. Then you do a real cutting. To validate the accuracy is right or wrong. So that's the part of the CPS. So the CPS actually, you have the physical model, you have an AI model, you combine together. Together with optimization, you can solve the problem of machine. So what is the next? If you have a CPS, what others we do in our lab, we have this kind of AI eyes. We can take the picture during the machining. We can use the stitch method to let the tool rotation. Then we can take a lot of picture. We can make the panorama of a tool. Then we can locate where is the tool wear. And we use UNet to separate the tool edge and the tool wear into this part. So in terms of this part, you can clearly see that we only capture the tool edge. And then all these tool edge, then you can use scanning edge detection to find the profile. That's one typical example that we use in AI manufacturing, which we use image to calculate the tool weight. But it is online, right? Because when you do the cutting, you cannot take the picture. You need to rotate the tool and go to a platform. So we still have this kind of, use the vibration and the sound and the spindle current to estimate the tool weight. But this one is very interesting that I'm sorry, it's maybe. 明明你也很爱我，美丽又爱不到结果。But if you could do something like that. 明明你也很爱我，美丽又爱。明明你也很爱我，美丽又爱不到结果。But without using any issues. You take the sound and make it into a spectrum. It's like you have an image. From the image, you can train your program to take some of the background noise like music and only contain the one that you want. What we want to do that is that in real factory, the noise, the background noise is very high. You need to train that your microphone not only receive your cutting sound, but also all the background noise. So in order to perform a better AI modeling, you need to use AI to filter out all this background noise. So this is the one we so-called AI skin that if someone touch you, you know, so you have this kind of AI skin, use the SVR. And we have robotics, the space accuracy, prediction, and the compensation. So that's a good conclusion. Actually, Microsoft says that the industrial metaverse is a human and the AI incorporated to design, construct, operate it, and optimize the real and the virtual world. The industrial metaverse probably is the next step because it's more like the virtual world incorporated with the real world, and you need higher computational power. Digital twin could interpret very differently in different areas. Then from machine, it requires different domain knowledge. Domain knowledge is somehow very important in order to obtain your optimization result and explain your optimization result. AI grounding is happening, but it still requires more advanced technology like autonomous learning. So at auto parts, I don't have time to translate all these in English. So it's a one that very now lab and I will talk in English. So we have a stage one which is not data progression, and this is the one that we have in our lab for the edge computing. So we can have this kind of relation input, we can have this kind of raw input, and also this kind of this talk, with this video, I will conclude my talk. Thank you very much.
Thank you for Professor Tsai for this speech. Due to time limit, we open to question or discussion with Professor Tsai.
Thanks for your very nice presentation. It's surprised that you have done a lot of job that combine AI technology with your CNC cutting. I wonder how's the actual application of such a kind of technology to domestic uses. Is that popular or still need time to absorb this kind of technology?
For domestic machine tool, now we are working with the Dongtai. We try to, apply our technologies for the 3-axis machine. For 5-axis machine, it is more complicated. It's underdeveloped, but for 3-axis machine, it is well matured. And the Dongtai will cooperate with one typical machine tool to validate all these concepts. But the academic level is somehow you require a lot of modeling methods, and you need to, put some sensor on the machine tool, and they need to have a full machine tool for your experiment. Then you can do something like that. But we are working on it. The one that we solve the problem is Yongji. We use the cutting dynamics top solver tool from. That's already done. Thank you.
Any question?
Thank you, Professor Tsai. You are always my research mentor. So I try to pursue you, but I still cannot see the tail light. Okay, so it's a great presentation, I would say. I have a question over here. It's about the AI model. For the manufacturer, we don't have enough data. This is always an issue. Do you think a mathematical model can help for that? Because you mentioned about sometimes you use a mathematical model to compensate some part of the unknown, and eventually you create the gray, I would say gray box, gray model, eventually push to the limit. But my issue is a lot of other manufacturer field don't have enough data. So could you have any comment on this? Thank you.
Okay, that's a very good question. Actually, for this kind of cutting mark, we have different kind of approach. One is the supervised, this is like a mass RCM. The other one, we cooperate with the professor in the computer science engineering, and he uses autoencoder. That means you only have a regular data. You train your model. They put the defect data. When they compare, then you can identify all the cutting mark, and you put the identified cutting mark on top of your normal figures. Yes, that's one way that you want to deal with this kind of data imbalance. Another one is that since your virtual workpiece is so accurate that it can put a lot of defect. Like I can put some of the friction parameter into that model. We can create some of the vibration signal into that feature. Then we can use that kind of a virtual diagram to train your model. Both are underdeveloped, but the result is okay. So far, the result is quite promising.
In closing this section, let's thank Professor Tsai for this essay. Thank you very much. Next, meeting will introduce the tour for tomorrow.
ladies and gentlemen, before lunch, we are going to announce the tour information. The tour schedule has been changed, so we want to invite you to join the new tour, one-day hot spring trip in southern Taiwan. So in the morning, we arrange to visit the most southern part of the Taiwan. And there will be a sashimi feast for the lunch. Yeah. And in the afternoon, we arrange to have a hot spring trip. If you want to know more information, please check it out at the registration counter. Yeah. And now, if you need the staff to lead you to the restaurant for lunch, please follow the staff outside by the counter. Thank you. Enjoy your lunch.
不是电视，不是电子纸，这好像是一个一个 LED 耶，好巧哦。
这个底到底是怎么？哦，真的很气他，那是底盖起来，那底是，我是什么？请哦，就挂掉，它就挂掉了，它真的就是直接挂。我在帮你换钱的那个，对，它开出不能用了，可是它没电，就超快，你到底知道吗？之前刚把这拿掉，而且我刚才重查，我拿了一个超细的，我教授就直接扎进来了。所以这种是他们的，他也不想开始机电脑，反正呢，我还想说先开的时候，就那是 OK 的，可他一样很高，我就不行。那我昨天也是，他可能昨天是没电，然后没电，然后他那个里面就是长电池，全部是上，然后只有2颗已经踩过了，然后我就想算了，我那种装的都是显示1颗，那2颗都没电。我们那边昨天那边都有点这样。至少结束了。我跟你讲，刚刚那个台大的教授跟那个日本那个教授，他们做东西都是刚好都是因为要点到的是那个色身上的教授，本来是那个教授不是那个说实话的教授，虽然他那个是一组，好像都是一组一组的，像那个是教授，他好像就是跟一个也是，对，在帮的，对，没有，主要是刚刚就有问过说，不会不用看情况，他说要查。就是自己看看可以，可是讲真的，你看的，如果你做的东西跟他很像，我就完蛋了，我就要查询。对，过了。我那天不是讲台大那个解放，帮我当我写的。对吧？不是。我刚不在打电话，我还没有给你。 可是它好像又少啊。手机的，这是水泥的，这个没配的。喂，那我把设备都测一测吧。我们是现在就要把它测出去。
他说这一间12点半要测掉。
好，对吧？12点半之前。
他说可以到。
那么差2点就啊？有，哎，可是你有没有学长教？
没有。
啊？有啊。好。你讲。没关系，我们会处理。没有了，我们一人一份，我的给你吃了。没事了。好，拜拜。